In this video, we're going to go over the solution to problem number 2 from the 1987 Electricity and Magnetism AP exam. So here we have a square loop of wire with a given resistance in the plane of the page, and notice that there's a magnetic field pointing out of the page that is toward the viewer, and at time 0 the field strength is 2 Tesla, and then it decreases as an exponential decay. So Part A is determine an expression for the magnetic flux through the loop as a function of time t. So that flux is a combination of the area of the loop and the strength of the field through the loop and the component, the perpendicular component of the magnetic field vector in the direction of the area vector of the loop. So first we have our givens, and the equation for magnetic flux is area vector dot magnetic field vector. Keep in mind that the area vector is going to be perpendicular to the plane of the figure, in this case the plane of the square. If it was a surface, it would be normal to the surface, but in this case everything is fine. The area vector is in the same direction as the field vector, so the magnetic flux is simply the product of the magnitudes of the area and the field. So eschewing units, we plug in our field, and the area is just the area of the square, which is L squared. So the question is, what is the what's the flux through the loop as a function of time t? Well, just plugging in our numbers, we have our result after we multiply things out. And notice in this case I did put in my units in the denominator. In the official solutions they didn't do that, but I think it's actually a good idea in this case. So part B is indicate the direction of the current of the induced current through the wire, in the wire. So let's see now. We have a magnetic field whose strength is undergoing exponential decay. So what that means is that we have the magnetic flux out of the page through the loop decreasing as a function of time. Well, Lenz's law says that there's going to be an induced current that will result in a kind of restoring of the status quo. So that means that the current must be such that the magnetic field inside of the loop would end up being out of the page to try to kind of restore the status quo of keeping more field out of the page. Well, by the right-hand rule, that means there is going to be a counterclockwise current. So if you need to go back on any of that explanation, either rewind the video or pause and read through the explanation. But moving on to part C, determining an expression for the induced current in that loop as a function of time t. Well, here we have Faraday's law, actually a combination of Faraday's law and Ohm's law. Current is EMF over R, and according to Faraday's law, the magnitude of that EMF is d phi dt, the rate at which the magnetic flux is changing. Technically it's E equals negative d phi dt, but in this case we're just plugging in the magnitude because we don't really care about the direction of the current. We care about its strength because, after all, we've already figured out the direction. So now, plugging in our equation for the magnetic flux, in other words, what we got in part A, we take a time derivative of that. So after applying the proper chain rule, we end up getting an expression of, for the magnitude at least, of 0.12 amps times e to the minus 4t per second. So there is the magnitude of our current as a function of time. And notice that as time goes onward, that current is also itself going to decrease. What about the total amount of energy dissipated as heat during this time? Well, what we can do is okay, the amount of energy, the amount of current is changing, but the total amount of energy is just going to be the time integration of the power. In other words, power is the rate at which energy is dissipated, so that means the total amount of energy is going to be given by the integral of power with respect to time. Well, we have an equation for power. P equals I squared R. Well, we have PIV, and we recognize that V equals IR, so that's what we need here because we already know the resistance that's given to us. We know the current because we just derived it. So now we're ready to set up our integral. where we plug in I squared r, with I being what we just found. So this result right here, this is the equation for power. This is P of t right here. So this is what we're going to plug into our integral. And upon doing that, we get the result of 0.011 joules. So about 1.1 centijoules, if you like using Greek prefixes in funny ways here. Now, interestingly, I got a different result than what are in the official solutions. So one of us plugged something in wrong. So I believe that it was they who plugged in something wrong, because their answer was 0.108 joules, and in this part right here they had 0.864, but I think there needs to be this extra zero here, because this 0.12 squared is 0.0144, and I think they might have forgotten that zero in front, and that would end up accounting for the other discrepancies. So if you see somewhere else where I may have made a mistake, then please let me know in the comments, and if you are one of my students, then you will get a bonus point for your troubles. Oh, and I do want to go through where they allotted the points on this before I forget about that. Going back to part A, there's your review of the problem. Part A, they gave 1 point for plugging, at least for using the equation for magnetic flux. You also could have done it as an integral, the integral of b vector dot dA vector, but in this case everything is constant, so I did not need to integrate. And then they gave 2 points for plugging stuff in. They gave 1 point for plugging in the L squared, and they gave 1 point for plugging in the magnetic field. And then finally, they gave 1 point for the answer. However, they did say that no points were awarded for going from integral of b vector dot dA vector to a time integral, because the time integral had nothing to do with this. Now, part B, they gave 1 point just for a statement of either counterclockwise or for arrows indicating the direction. Technically, it should have just been arrows, because that's what they asked for. Part C, they gave 4 points for the total part. They gave 1 point for an indication of Faraday's law. They gave 1 point for plugging the numbers into Faraday's law. They actually did want the negative sign on this, but I think in this case it really didn't matter. So I don't know whether they would have given the point for the lack of negative sign. But technically it should be a negative sign, but I figure we were just looking for the induced current strength because we had already calculated the direction. But anyway, they also gave 1 point for the use of Ohm's law, and they gave 1 point for the correct final answer. Now in part D, the way these points work, there were 6 points total for part D. 1 point for using P equals I squared R, or an equivalent expression with correct ways of evaluating it. 2 points for the overall integral. 1 point for an indication that you needed to integrate, and 1 point for correct limits. This is often how they do things with problems that require integration. And then they gave 1 point for the correct plugging in of the numbers into the integral, 1 point for a correct evaluation of the integral, and 1 point for the correct final answer. So that's how they awarded the points on this. So again, if you have any other questions, please let me know. Thank you.